Welcome to episode 2 of the AI learning series. Today we'll do an intro to AI. It sounds that AI is a deep topic, so 45 minutes is not going to do it justice. But we'll touch on a series of topics, and really it's a way for folks to get dip their toes into AI in the world of AI. Also a way to fire up your imagination. If you have questions after this, or if you have an idea for something you would like to see us dive more deeply into, please let us know. So today I would like to talk about the why of AI. Where does AI come from? Why is it so popular right now? But also why AI for our customer base in our market. I'll talk a little bit of, I'll transition to what AI is in our context. Very quickly talk about how we implement AI for Apollo 4+, and get into some of the details about how that's going to look in the near future. So first, I'd like to throw this slide up. It made more sense maybe a couple years ago when all these concepts were kind of fuzzy. But it's good to get a "you are here" thing. Today we're going to be talking mostly about deep learning, which is the popular AI thing, the neural network-based AI. Deep learning is a part of machine learning, which is a more general concept where you're using statistical techniques, to produce a solution. Both deep learning and machine learning have learning in the title, meaning that you start from kind of an unlearned set of either parameters or neural networks, and then you use data programming techniques to learn, to tune those parameters to value, to the right values. And then the biggest thing is AI, right? Artificial intelligence. And that's anything, it's really kind of a fuzzy concept, but it's anything that emulates human or even animal intelligence. I like to say animal intelligence because sometimes the AI that we do is useful, even if it's, say, kind of a pet behavior, a dog behavior, or something like that. Okay, so with that in mind, we're going to be talking about deep learning, which is the focus of our team here at Ambiq. And let's get right into it. So why? It's tempting to think of AI as just another kind of hype curve buzzword, but the reason it was maybe 5-6 years ago it was, but the reason it stuck around, it's actually becoming widely adopted everywhere, is because of this. It's an easy button, right? It's the easiest way to do hard things, and let me explain what I mean by that. Take computer vision, which is a really difficult task. Since computers were invented and you can plug a camera into one, data scientists and computer engineers have been trying to use software to classify objects, to say, hey, this is a person, or hey, this is a cat, or this is a car, and so on. And so that's been going on as long as computers have been around, at least since I was a kid back in the Stone Ages. And if you look at this graph, which is starts in 2010, think about 30 years before 2010. All these computer scientists, all these PhDs at MIT and Berkeley and across the planet were writing traditional software methods, algorithms based on traditional software methods. And I'll talk a little bit about what those look like in the next slide. But after those 30 years, the best they could do out of this, classification task was around 25% accuracy. So you showed it 4 things. One of those things would be misclassified as a cat. Interesting, but useless, right? If you don't have a very high accuracy, the algorithm is just not it's not going to be used. And we all remember maybe in the early 2000s where, like photo managing software started saying, hey, this picture looks like Jessica. Do you want to, and then you would tag it and it would do an okay job, but really not that accurate. So that's 30 years of unceasing effort. So many grad students beat their heads against this. And in 2012, AlexNet comes online. And AlexNet is really one of the first image classification neural network-based AIs. And very quickly, in a matter of 1 year, this challenge went from 25% inaccuracy to just 15%. And then the next year, it dropped again. And within the span of like a blazingly fast, remember 30 years, 3 years, deep learning solved basically the image classification problem, to the point where if you put this task up against this AI, up against a typical human, the AI will beat it. So something that was intractable, and we'll see why it's so intractable using traditional methods. You use data-driven programming, AI, and suddenly solved. And it's not that I'm lazy. It's not that the interesting stuff stopped in 2017, right? And I just didn't want to look for more data. It's that this challenge is over. You beat it. So now the folks who set up these challenges have produced new challenges. This is considered solved. And so what takes us from the blue to the white in this graph? It was the switch from traditional programming methods where you just write a bunch of rules. And if you miss something, if the cat's looking at you sideways and you didn't pick that, then you write a rule for rotating cats. You went from that approach to data-driven programming. The software for neural network architecture is actually, the neural network is probably defined in a couple dozen months. All the software around feeding the data and calculating error adds a few hundred more lines. But instead of millions of rules, you have a few hundred rules, code, and then you feed it data. And the rules are about how to learn the parameters, the actual rules from the data. And then the next step is really using AI to produce AI. So you write even less rules. In fact, the proper AutoML, you just show it the data, and the AI will figure out, oh, this data has this kind of shape and this kind of correct characteristics. I will design an AI that produces a right result. So that's the next stage, and that's starting to happen. And so that's AI in general. So AI for endpoints, AI for the market that Ambiq is in, is exploding right now. And for the longest time, for the first 5 or 6 years of this AI explosion, the focus was on very large models, and it still is. Like if you read the newspaper, the layman newspaper articles about AI, you'll see a lot of talk about DALL-E and speech recognition and GPT-3. These are all multi-billion parameter models. They're huge, and they're really designed to run in data centers. If you go to an AI conference, all you hear about today is REXs, recommendation systems, because that's what makes money for the Facebooks and Amazons. And so that's where all the focus was for a very long time. There is a group of researchers at MIT, Berkeley, Carnegie Mellon, and so on, that have decided that small is beautiful, right? That putting AI in very, very constrained spaces is also worthy of research. So that is really driving that kind of innovation in the algorithmic and compression space of AI, is driving this push to small. When you add that to, you put that and you wrap it in a kind of a mature software stack, which finally is happening, you get an ecosystem. So you see all these startups like Edge Impulse and so on that are capitalizing on this and making it easy for subject matter experts to produce their own AIs. And then finally, you have something like an Apollo 4 Plus, which just sips power. And so where before AI, yeah, you could do it in a constrained space, but you would just burn through your battery. Something like Apollo 4 Plus makes it practical to put on a wristwatch or in a fire detector or so on. So these three things are coming together and just really creating a burgeoning market. And, Ambiq is perfectly positioned to take advantage of that. So how does it work? Let's, I alluded to some of the data-driven versus rule-driven. Let's talk about that. So I didn't want to, there's a lot of images on the internet that will kind of teach you this, but I didn't want to look for copyrights and so on, so I used my headshot. So let's say that your boss came in and said, hey, I need you to write a function that identifies Carloses, I don't know, people instead of animals. So you show it a picture and it decides that picture is Carlos, not Carlos. Right? So me being a naive grad student or somebody who's just starting out in this field would say, okay, well, Carlos's eyes are always this far apart, right? So maybe you write a rule that says, okay, that's the distance between eyes. Carlos has a pretty big nose. So let's put the nose into the rule. So you put a little distance from eyes to nose. And that captures a few of them. But then, I twist my face and all those geometries change. So maybe add some more rules, right? Mouth size and so on. And then somebody with my nose and mouth size shows up. So, well, what else identifies a Carlos from a not Carlos? Maybe it's the chin being all round, and maybe the eyebrows are weird. So you just keep adding rules. And the way this works is you actually have to add millions of rules. I mean, think about, you're looking straight at the camera there. What if I twist? What if I'm smiling and so on? So this is a traditional approach to programming. We all do it. Those of us in the audience who are programmers, we're used to the if this and this and this and this. And so over the 30 years of development here, there are ways to systematize these rules, to capture them as data. But that's still rule-based, right? You still have to find kind of some expert system and capture that. And that starts kind of crossing into the border of AI, but not the one that we're going to talk about. What we do in deep learning is we just show, we create a neural, like it's a snippet of software that defines a neural network, that series of bubbles on the side there. And then we show it data. We show it not just a little bit of data, millions of data sets. Like if I were training a Carlos, not Carlos, I would go to the FaceNet, which is a big 10 million face data set. And I would say, all of those are not Carlos. And then I would show it maybe 1,000 pictures of Carlos and say, those are Carlos. And you feed it into the network. And eventually the output will be yes, no, Carlos, not Carlos. And the other thing I do is I'll take that picture and I'll rotate it and I'll shmoo it and I'll add noise to it, because a camera is not always going to be perfectly dead on. So it's called data augmentation. So you take the data that you have, the 10 million pictures, you fuzz it up, you feed it. And the reason that works is because the neural network is designed to find Carlos, not Carlos, despite all the noise and all that stuff. And you don't tell it how to do it. You just say, hey, this rotated image is still Carlos, and it will adjust and learn that rotated image is Carlos. That's the comparison of AI versus traditional programming. Okay, so how does that work? And let's say that I want to train this undifferentiated dumb model to identify that is a picture of a dog and not a burrito. So you start from an unlearned state, and what you do is you randomize all those lines or synapses between these neurons. You just kind of assign random values to them. And there's all these little techniques for doing that. But when you have a random neural network and you show it a dog, that's called the forward pass or the inference pass, it's going to get it wrong. It's going to say, okay, maybe that's a burrito or something else, who knows? It's just completely random. So you do that, and then you compute the error between burrito and dog, and then you back propagate. Because what you're doing is you're going through each one of those neurons over the synapse and say, hey, if you adjusted the synapse this much, the probability of you getting the right answer would improve a little bit. And you don't want it to improve infinitely. You could do a backward pass that would get the right answer. But that means the next picture that you showed it would get the same answer probably. So you adjust it a little bit, This is a process, it's a mathematical process. It's called stochastic gradient descent. And the stochastic part means it's random. The gradient is refers to the error, right? So if you visualize this in one dimension, there is a set of parameters that minimizes the error, right? And what you want to do is you want to find the set of parameters, a set of neural values that kind of move you towards that minimum, right? So that's one dimension, but usually you have something like 17 or 18 dimensions. So just visualize it, if you will, for a second, like a 17-dimensional space, and then you have an algorithm that's finding minimum in that space. And you do that once for the dog, and then you do that for every image that you have, right? You just do a for loop, everything. And you do that once, and then you do it again. That's called an epoch, and then you repeat epochs until your accuracy, this compute error, stops going down. And that's when you declare your model learned, trained, or you give up and you say your model is crap, and then you restart with a different architecture. So that backward propagation is the magic. Also, it's a reason that NVIDIA stock is so high, because computationally it's insane. With acres of compute sometimes. Okay, once that's done, you have a trained model. Now that forward pass, very simple, much easier to do. It's what you can run on an Apollo 4 Plus. You wouldn't want to do stochastic gradient descent on an MCU. So you take that model, the trained model, you have neurons, you have that all have values, and you put it into your Apollo, and then you do this inference step. And we'll talk a little bit about some optimizations you can do around memory in a different presentation. But this is what you deploy, basically, at the end of the day. It's a trained, fixed model that is not learning anything else. I should say that there's some research going on what's called endpoint training. The tiny ML community is working on this. Some of those same researchers that I mentioned earlier, Songhan and so on, are ready to start talking about. And the reason you want to do online training or edge training is because you want to tune your model, in some cases, to your user. So human activity recognition trained on a public data set may not recognize your particular gait. So if you're walking and you get it wrong, you tell your watch you got it wrong. If you have online training, edge training, your watch could get personalized to your particular physical characteristics. Now, because this is an intro to AI, I do want to kind of cover 3 things that you will hear about constantly and gets confusing. You'll often hear about CNNs. So a CNN is a convolutional neural network, and it's I showed you the architecture. That's kind of a toy architecture. There's a lot of varieties of neural network layers that connect to each other and how they connect. CNNs are one kind, and I have a slide for that in a second, so I won't get too much into it. But it really is about image classification. It's when you have, if you think about an image, no matter where in that image a nose shows up, it's a nose. So you want almost a little mini neural network that knows nothing but noses. Not that you told it. Remember, you're not setting up these rules. You're just saying, I'm going to set up an architecture that is inclined to find noses, right, or find features that are small. Another thing that happens very often in the space is that there is a time component. So imagine that you're looking at a ECG, right? So ECG is a time series where your heart's doing all, that stuff. And just looking at like one slice of that is not enough. You have to know what happened before. So your neural network has to have a little bit of memory about what happened the last few milliseconds or last few seconds. Convolutional neural networks don't do that. It's a slice, right? And just one time slice. So that's what a recurrent neural network is. One kind of neural network, a recurrent neural network, is an LSTM, long short-term memory. It's very popular. And what it does is, those layers, imagine those layers, and I'll have a slide for this. They're not just getting data in, they're feeding data back. So and that feedback loop is actually learned as well. So that the thickness of that line is learned. So it's useful for things like the ECG, but also when you're speaking in a sentence, you can't look at every word. You have to look at the last few words. And then the magic of these all these recent AIs that seem like they're writing cogent things, right? They're writing paragraphs and articles, is that the memory goes back really far back. And so you actually need a new architecture for that, which we won't cover. It's called a transformer architecture. The reason we won't cover it is there is no chance of me getting that on Impala 4 yet. Okay, and then a really interesting, very simple to understand model is an autoencoder. So autoencoders, actually, they're kind of like funnels. They funnel complex data down to simple data, low dimensional data, and then they funnel it back out to the original data. And what the network learns is how to do that. And so that means it's useful for compression, because audio compression, you compress it down to very low dimensional data. And then if you did it right, you can just transmit that low dimensional data. And the decompressor will theoretically do a good job. They don't quite work that well because our ears are super good. I'm not going to get into this. They can get pretty deep. This is an example of how a convolutional neural network works. Let me walk through it, right? Traditionally, when you think of a neural network, every pixel that comes in from that image of a car will go to a neuron. And what a convolutional neural network does is it takes like say a 3x3 or a 5x5 kernel, convolutional kernel, and schmooze it across the image. And it does that, it overlaps a little bit. And the idea is that small thing will pick up details in the image. And you don't have just one, you have a bunch of them. And so that's this part here. You pull those results, meaning each one of those kernels will go into like a fully connected pooling layer. Maybe you do another convolution and so on. So how many of these you repeat is kind of a black art. And then finally, you get a layer that should be firing, the neuron should be turning on and off for different features. Like I found an eye, and then maybe another neuron says, hey, no, I found 2 eyes. Okay. And then maybe the third neuron goes, no, I found 8 eyes, right? So okay, now we're looking at a spider or a car. That's how a convolutional neural network works. It's defining kernels that are just set up so that they find features. Again, you're not saying, hey, look for eyes. Just saying, find something interesting, because at the end, that's going to be relevant. At the end over here, where it says car, truck, van, that's going to be relevant to a correct result. So a recurrent neural network, the concept here is the output of that goes back and cycles, right? So it's a cascading neural network. And then finally, autoencoder is one of my favorite things for constrained environments. So what's happening here is you're taking a high dimensional input. You're taking something like a picture, for example, or a song, and then you're just passing it through successive smaller and smaller layers until you get to the middle. And then you kind of mirror that on the output, and then the model will compare the output to the input. And that back propagation will pick the right neural network weights to make the output and the input similar. So 2 things happen here. One is, if you did it right, and the output and the input are the same, what you're saying is that little pink box in the middle, the code box, actually captures all the relevant information from the input. So if it's a song, it's probably capturing notes in the song. If it's an image, it's capturing things like eyes and ears, and knows what an eye and an ear look like. And so you've seen examples of this. When you've seen generative art, like DALL-E, for example, DALL-E is a complex case, but the earlier versions of DALL-E, what you're doing is you've trained something like this on, 10 million images. Then you throw away the front part. You throw away the input part, and you poke a neuron in the code layer. You say, okay, I want eye, right? And I want an eye and a horse. And then so you find the pixel that says horse, the neuron that says horse. You find the neuron that says eye, and maybe there's a neuron that says white. And then the output should look like the eyes on a white horse. So that's one way to do it, to use this. You can also use it to compress. So imagine that you have voice coming in, you compress it to very low dimensional, very low bit rate code, and the output should sound like voice. Now, in practice, I've listened to these autoencoders, even the state of the art, not so good. So visual, like our brains are set up to interpolate visual kind of imagery. And so if something is wrong, and the face doesn't look right, your brain will fill in the mistakes. Audio, our brains are not forgiving. You will hear every glitch. So this is better suited to maybe not audio, not yet. So that's it. I think that's the intro to AI. Those are the basic concepts that will make you conversant. Now you can go into a coffee shop and talk about convolutional neural networks and how they apply to auto. I don't know. Just mix and match the buzzwords there. Okay, so how do we implement that on our environment? Okay, so let's actually, before we get into Apollo 4 Plus, let's talk about, in general, what does this look like? You have to write some code, and so when we say implementing a model, what we really mean is you define that model, like the inputs, the neural architecture, plus you have some trained weights. When you create a model, it's the architecture plus the weights. So to do that, you have to train. Until you do that, until you've trained, all you have is a model definition. You don't actually have a model. So those are the three, like I labeled the three big parts of code: the feature, data extraction and prep, the neural network definition, and then an important part is that error calculation. It's not just like a diff, right? It's actually, it could get very elaborate. And if you get any one of these things wrong, the model is not going to be state of the art. It's not going to be the best. The good news is that writing this code, the coding part of it is not that complex. Like here is the entire model for a speech enhancement. So there's something called Tiny LSTM, which takes noisy speech, identifies the speech part, masks everything out. It's almost like automatic noise cancellation, but it lets the speech through. So really difficult task to do. And if you look at, this is the entirety of the code that defines that middle part, the neural network definition. So you calculate your input, your MEL scale. So you go to MEL spectrograms. You define a couple of LSTM layers, which are like here the recurrent neural network that does this, and then a couple of dense layers that do the actual anti-mask calculation. So I purposely took this piece of code because it's a bit misleading, right? This model is super simple. The feature and data extraction and the error calculation are actually 1,000 lines each. So often the model definition is pretty trivial. And what you'll see in data scientists is that once they get the pipeline going, they will mostly play with this part because it's so easy to change. And then they'll have, it's like, let's try this, let's try this, let's try this, and they'll just keep running it until they get a good architecture. All right. So simple, right? Everybody can write data science. And more generally, this is what it looks like, right? You're on the left-hand side here. You start from your data. You'll learn very quickly that if you don't have a good data set, it's hard. So depending on your domain, there are probably some very popular public data sets that you can get access to, or actually pretty cheap data sets, $50 licenses and so on, because they're set up for research. And then you start looking at what kind of deductions you can make from that data. Maybe you add your own data, like we're adding Carlos to the ImageNet data set. And then you pick an architecture, you look at the data, say, okay, maybe this is suitable, the CNN's will be suitable. You pick an architecture from something that's there, maybe you modify it, and then you start refining it. You run the model, you see errors. You don't actually run it on the entire data set because that would sometimes it takes days, right? You run it on a subset section of that. Once you're pretty happy with the accuracy that you're getting, you're ready to start going to the full data set. So there's a step here called hyperparameter optimization. And the reason it's called hyperparameter optimization is that those weights, because of history, the weights in the neural network are called parameters. So of course, training is optimizing the parameters. Hyperparameters are parameters about parameters. So things like your model architecture could be a hyperparameter. How quickly you learn is called forget the term, learning speed or whatever. How much you adjust the gradient every time you go through your learning rate. I'm sorry, black here. That's a hyperparameter. How you partition your data set. There's all these hyperparameters, and finding the right set of values is pretty hard. So there are algorithms that do that for you. Once you're pretty happy with that, you do the training. That could take some days. You could get some coffee, Paris. And if you're not happy with it, you go back. So there's back arrows everywhere here. This is an iterative process. Once you're pretty happy with this, you'll compress it. So that's something that we need to do generally to get things to fit on our environment. There are compression techniques that happen during training. So one of the compression techniques is you take these models, right? That LSTM model that you just saw, the data that it works on in the training side is real 64. So it has, audio is both phase and amplitude. So you actually use imaginary numbers during training. But we don't want to run that on Apollo 4 Plus, right? So you have to translate real 64 down to int8, which is what we operate on Apollo 4. So in that case, in that model's case, part of the reason for the complexity of the model is that the developer is adding quantization-aware training. So they quantize during training, not after training. And that will that'll make your model lose less accuracy. Now, because when you quantize a number, you will lose accuracy. So if you don't do that and you do it after training, post-quantization training, you will lose accuracy, but it's generally pretty good. So compression is one way of doing that. Sorry, quantization is. Another two very popular things that we do in the space are pruning. Turns out that sometimes those neurons aren't doing anything. After you've done your whole architecture, you look at a neuron, it's just sitting at 0, right? So you find those neurons, you get rid of them. It's more complicated than that because it's a matrix and CPUs like to do matrix multiplies. So you can't just get rid of the 0 and hope that it works. You have to kind of get rid of blocks. And so you'll lose some accuracy. Maybe you just delete a layer and see what happens. And distillation is another really popular technique where you take a very small model and you train it using the big model, right? So it's a student-teacher kind of model. Okay, so you compress it. Compression will get you between 1/4 to 1/8 of the original size. And then you convert it to something you can actually execute. And so like this part is all on your laptop or on your desktop or on the cloud. And you're using tools like Python, TensorFlow, Keras, which is what you just saw, where the layers you were defining. Jupyter is an interactive tool for running Python. So once you're ready, you hit make, you send it to your EVB. And this stuff is where we're focused on at Ambiq, right? We have our data scientists are actually end-to-end data scientists, so they're writing the models. But where we differentiate greatly, really starting from the compression step all the way through deployment. So that environment is more C. We have to do C++ because TensorFlow Lite is in C++. Some of the other tools that we use are C++. We use Ambiq Suite and we wrap it in a SDK called NeuralSpot. And so that's what we call a runtime. The thing that's actually running the model is a runtime. Okay, so this is the typical architecture for a runtime. You put in that user model, that LSTM thing, that Python code. You compile it down to a set of weights and biases, right? And what that looks like is, if you look at C, at the C that comes out of this, it's just a big long array, 60,000, 70,000 element array, maybe 200,000, right? Some of these models are 200, 300K. And that's it. And then you feed that array to an interpreter that's going through that array. It's doing computation in your input and spitting out an output. So that's a graph interpreter. In our case, what we're using is TensorFlow Lite for microcontrollers, which is a very popular tool in this space. Other tools are like Onyx Runtime, which is not supported quite yet. Glow is another way of doing this is ahead of time. So that, TensorFlow Lite for microcontrollers is an interpreter. It's actually interpreting that array. Ahead of time, compilers will actually compile it into a binary that executes. I've experimented with MicroTVM and Glow. They're not producing very performant results. I've talked to the people who are working on these. It looks like MicroTVM is heading in the right direction. Glow is by Facebook, so they just don't care too much about this space. So one of the models that we're producing for our kind of go-to-market is actually a hand-coded model. So you use a top, you train using TensorFlow, but then the output, what my data scientist is doing, is actually writing C that implements that model. Super cool. And the reason we're doing that is so we can compare power and latency of TensorFlow Lite Micro versus hand-coded versions of the same thing. Well, thank you all. I appreciate your time, and as always, reach out to me if you have any questions.